Elliptic curve cryptography, so EC cryptography, or sometimes called ECC, elliptic curve cryptography, all three letters together. It's an alternative to the RSA algorithm. So RSA relies on the difficulty in factoring large prime numbers for its security. That's its trapdoor function, essentially. Elliptic curve cryptography relies on the difficulty of traversing graphs that look like the one I have in this image here. There are very specific curves with specific formulas. The curves have names applied to them. There'll be a mathematical formula which produces the curve, and there will be a generator point at which you start the curve. Now there are some rules for how we traverse. Your private key in this is just a big number, just a number. And then the public key will be where you end up on this curve. So starting at this generator point, if your private key was 3, you would follow some very specific rules about bouncing on this curve, and you would bounce 1, 2, 3 times and end up on a different place on the curve. And that point where you end up is your public key. And it's just a number. The coordinates represented as a single very large number. So if you give somebody that point and say, hey, this is my public key, it turns out it's really, really difficult to determine how many jumps along the curve it took you to get there. Just trust me on that one. The math looks much more complicated than my very brief description there. So here's that kind of mapped out. I've got my generator point, that's my starting point. So I would bounce over on the curve, and if I go out of bounds, I gotta go down instead of to the right. There's very specific rules about how you essentially bounce along this curve, so you end up at a point which is your public key. So given a private key, you can always derive the public key, but given the public key, doing the reverse process just is not feasible. That's where it gets its security from. In practice, the tools use shortcuts, I guess I could say. They're not bouncing a trillion times to try to find the public key. There's some very interesting mathematical ways that the cryptographers came up with to compute this extremely quickly. So it's easy to go forward, very, very difficult to go backwards. And that's where its security comes from. So let's just take a look at creating a key. Let's create an elliptic curve key. So let's make sure that we're in our home directory. I'm in home Ubuntu, and I will run ssh-key gen. So SSH, the secure shell, it's got lots of cryptographic capabilities inside it, because to be secure, it has to understand public key, private key cryptography. And we're going to say -t and type ED25519. So the type, it's an elliptic curve, and this is the name of the curve. It's got a very specific formula. This is one of the most popular ones. If you're using transport layer security, so HTTPS, this is one of the curves that your web browser and the web server, they have to be able to support. So let's see how long it takes to create this key. Enter the file where we want to save it. I'm okay with that, so I'm just going to hit enter to keep the default. I'm not going to enter a passphrase because we just want to look at the key. Same passphrase again, just hit enter. So after I hit enter that last time, creating the key was super fast. Like almost instant. All my computer basically did was pick a random number between 0 and 2 to the 255th power minus 1. That's the gist of what it was doing. slightly more complicated, but essentially you're just picking a random number. So let's go take a look at that key. We see we've got a fingerprint of that key, and it gives us some random art. We are supposed to be able to look at that art later and recognize like, oh, that's my key. It's kind of another way like to generate a fingerprint of the key. You can tell from my screenshot it's different from what's listed there. All right, so this is good. So we're in our home directory. I'm going to cd into the .ssh directory. So notice if we ls, we don't see the .ssh directory, but if I ls-al, I've got .ssh there. So I'll cd .ssh, look at what's inside there. And what I'm going to scroll up. What did it tell me? It told me it saved my public key in that file .pub. So let's take a look. Two files because they're key pairs. We've got a private key and the public key. So hard to interpret, but I'm just going to cat ID and hit tab. It says begin open SSH private key. Similar kind of format to our RSA key. We had those dashes and begin and dashes and end. So common convention, just something to be aware of. So it's hard to interpret this data. It's just kind of compressed, but this is the key. I would not use this private key because I just showed it to you. So we can take a look at the public key. That's what we can send to somebody else. So it's named ID ed25519.pub. So I'll just cat that out. Cat ID underscore dot tab. There we go. There's the public key that I can send to people. So with that public key, me and somebody else, we can encrypt data for each other so we can transmit information, including temporary keys. So again, asymmetric cryptography, so RSA and elliptic curve cryptography, those are the two most popular today. Their two primary use cases are signing files and exchanging keys. You typically don't encrypt like files on your hard drive using asymmetric cryptography. You would use symmetric cryptography for that use case. Even sending browser data between your web browser and the server, you're going to use symmetric cryptography. But how do you exchange that symmetric key? Well, you would use asymmetric cryptography to exchange those keys, and then you would use symmetric cryptography from then on out to actually transmit the page data securely. So there we go. There's a look at what the keys are. I just wanted to demystify the key because it's nothing super fancy. It's just a file on your computer. So we need to protect those files.